So in this session, we'll be doing the the IBDP portion of giant covalent structures. What are they? How they influence? Now, prior to going to this giant covalent structures, we have to get to know about that. How can we predict the bonding of the elements which are there? We see that the elements are wonderfully distributed in the periodic table in increasing the atomic number. We are increasing the atomic number, and we are placing the individual elements in different groups. Group number 1, group number 2, group number 3, group number 4, right? We're placing them in the different groups. Now, moving ahead, we have to know that we can predict what kind of bonding it will be uttering, right? Such as the group number tells you what? To group number tells you the number of electrons in the outermost orbit. So group number 1 has got 1 electron in the outermost orbit. Group number 2 has got 2 electrons in the outermost orbit. Group number 7 has got 7 electrons in the outermost orbit. Group number 6 has got 6 electrons in the outermost orbit. Group number 7 has got 7 electrons in the outermost, so 5 electrons in the outermost orbit, and so on. Now we know that. Let's test it. Suppose sodium. Sodium is 281, isn't it? So there's 1 electron in the outermost orbit. So sodium has to lose an electron, right? Because all these elements in this periodic table has got one mission. What's the mission they have? They have to be like the noble gases, right? Means 8 electrons in the outermost orbit. So this is a very important portion we have to learn. That suppose sodium wants to lose an electron, right? It wants to lose an electron. It wants to dump an electron. Now, sodium cannot just dump an electron anywhere. That's a very important factor to master, right? Cannot dump an electron anywhere. This is very important, that it has to have somebody such as chlorine who can gain that electron. Is it clear? Who can gain that electron? This is very important. Let's suppose chlorine. Chlorine is in group number 7, right? So let's check that number of electrons in the outermost orbit should be 7. So chlorine, if you see, 287. So it has to gain an electron. But it cannot just gain an electron lying idle. No electrons is lying idle anywhere. It has to have somebody who can give this electron. And who gives it? If a metal such as sodium is near it, then it gives that electron. And when it gives that electron, what happens? We form an ionic compound. That's a very important information we have to master. That we will be forming an ionic compound. Now, moving to this part, we have to know that if we see that when we see an ionic compound, right? In an ionic compound, we are seeing what? In an ionic compound, we are seeing that it will be attraction between the positive ion, electrostatic attraction, and the negative ion. And it is a bond between a metal and a non-metal. Now, we take the second scenario. Suppose chlorine. Chlorine has got 7 electrons in the outermost orbit. It has to desperately get an electron from a metal. Now, if there is no metal near this chlorine, what happens? Chlorine will be sharing 1 electron with another chlorine. And we get what? We will be getting a covalent bond. So that's a very important portion we have to master, right? It will be forming a covalent bond. Now, a covalent bond will be a bond between a non-metal and a non-metal. This is crucial, right? It will bond non-metal and a non-metal. So when we talk about covalent compounds, we have to understand over here that covalent compounds will be always will be sharing of electrons. And how to represent these covalent compounds or the covalent proton molecules? The covalent molecules we represent like this way, that we show it by sharing of electrons like this. And these are called as molecules. What's a molecule? Molecules are those which has atoms bonded by a covalent bond only. This is the first thing you have to master. What are molecules? Molecules are atoms bonded by a covalent bond only, number one. Number two, molecules contains a fixed number of atoms. This is also important, fixed number of atoms in a fixed ratio. This is very important. So if you see, when we talk about molecules, molecules are what? Molecules are atoms bonded by a covalent bond only. This also has to be satisfied. And it should contain fixed number of atoms in a fixed ratio, such as, suppose I'm taking H2O. In H2O, we see that, does it come under molecule status? Let's check. First thing is that, does it contain a covalent bond only? Yes, it does. Second, does it contain a fixed number of atoms in a fixed ratio? Yes, it does. 3 atoms are there. And the ratio is what? 2:1. So this is also a very important portion we have to master, that whenever we are seeing the molecule contains a fixed number of atoms in a fixed ratio. And molecules should have a covalent bond only. Now, this is the way we represent the molecules, isn't it? We show the sharing of electrons over here like this, and we show the sharing of electrons in this manner, right? We can write down the molecules. Now, moving to this part, you have to know about a very important information, that a molecule is attracted by another molecule. This is very important. A molecule is attracted by another molecule by weak forces of attraction. This bit is very crucial going ahead. Suppose you're taking chlorine, chlorine. If you're taking chlorine, 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 chlorine will be attracted by another chlorine, chlorine by what? By attractive forces, weak attractive forces, or intermolecular force of attraction we call intermolecular force of attraction. So a molecule will be attracted with another molecule by weak intermolecular forces of attraction. And thus, you'll be seeing that this intermolecular forces of attraction are very weak in nature. By nature, it is very weak. So thus, this bond can be easily broken down. So now, when we see the intermolecular force of attraction, this intermolecular force of attraction will be guiding what? All the physical properties of the molecule. This bit is very important. They will be guiding all the physical properties of that molecule, right? What are the physical properties we know? Boiling point, melting point, everything. Now tell me one thing, if the intermolecular force of attraction is stronger, more amount of energy will be needed to separate these two molecules. Now remember one important thing, when I take the board papers, I see that maximum people are doing a silly mistake. Maximum students. This is a covalent bond, right? In melting or boiling, we break which bond? We break bond number, tell me, we break bond number 2. Is it clear? Not bond number 1. This is clear to you. This is clear that when we see a molecule contains a covalent bond, and a molecule is attracted with another molecule by weak attraction forces, this intermolecular force of attraction. So the strength of the intermolecular force of attraction is very important. Why? Because that will be determining that how much energy we need to separate these two molecules. And thus the boiling point and melting point and volatility all will be depending upon the strength of the intermolecular force of attraction. And the strength of the intermolecular force of attraction are weak by nature. They are weak in nature. This is very important. We have to understand. They are very weak in nature. This is very important. That the covalent bonds are very strong. During melting, boiling, or volatility, we don't break this covalent bond. Never. Never ever. If I'll check the board papers, I see that this mistake is there. We break the intermolecular force of attraction. Intermolecular force of attraction. And the intermolecular force of attraction are weak by nature. And the intermolecular force of attraction depends upon what? The size increases by the size of the molecules. More the size, more. And hence, molecules have got very low melting point and boiling point. This is a very important thing you have to master. But you know what? There are other covalent structures, such as diamond. Can diamond be considered as a molecule? First, we have to understand this. Can diamond be considered as a molecule? No. Why? Although diamond has got a covalent bond only, it has, right? It has got a covalent bond only. But does it have a fixed number of atoms? What do you think? Fixed number of atoms? Does it have a fixed number of atoms? It does not. Why? Because in diamond, what's the structure? In the diamond, we have got one carbon attached to 4 other carbons, right? And that's not all. This goes on and on and on. Got it? Understood? This goes on and on and on, right? In a gigantic lattice structure. This is the thing we have to master. That in diamond, what's the structure? One, you can write down 1C, 4C bonds. They have got a covalent bond only, agreed. But does it have a fixed number of atoms as per the definition of the molecules we learned? No, it does not, right? Diamond does not. Why? Because diamond will be having infinity atoms, right? A small diamond, a large diamond, and they will be having a gigantic lattice structure. Now in diamond, you see that during the bonding, we know that we learned about the electrical conductivity. Electrical conductivity depends upon what? Electrical conductivity, if you see electrical conductivity, who are the carriers of electricity? There must be free ions or there must be free electrons. This is very important. Is it clear to you that there must be free ions or there must be free electrons? Any one of them should be present. This is a very important juncture we have to master, right? There must be free electrons or free ions. Now, moving to this part, we have to know that if we see that when we talk about diamond, in diamond all the electrons are are in a covalent bond, not free to conduct electricity, because diamond has got one carbon attached to how many carbons? Four carbons, right? And thus in a gigantic lattice structure. So we have to break this, all these millions. When we utter the word giant, we mean what? Millions of bonds. So we have to break all these millions of bonds, billions of bonds over here, millions and billions of bonds we have to break. And thus diamond will be having a very high, not high, very, very high melting point and boiling point. This is a very important structure you have to master. The diamond will be having a very high melting point, boiling point. Why? Because diamond has got a gigantic lattice structure. Giant. In chemistry, giant means what? Huge. Sorry, in real life, it means huge. In chemistry, it means what? Millions of bonds. So this is the thing we have to master, that when diamond, it will be having a gigantic lattice structure. And not as molecules, because molecules are having very low melting point, boiling point. See, water has got the strongest intermolecular force of attraction, but it melts at 0 degrees centigrade. See, quite low. Fine. Suppose NaCl. NaCl has got a melting point of how much? 800 degrees centigrade, approximately 1000 degrees centigrade. Because why? Because in molecules are attracted with other molecules by weak attraction forces. But diamond, although it's having a covalent bond, it does not have a fixed number of atoms. It does not. It has got millions of bonds, right? Isn't it? Infinity bonds. We don't know, right? Infinity atoms, right? Now we notice that if we go to the next structure, that is graphite. In graphite, what happens? In graphite, we'll be seeing that one carbon, it is attached to how many carbons? Is attached to three other carbons, right? In the form of hexagons, in giant layers. This utter word you have to do. In graphite, what happens? You can write it down 1C, 3C bond. Don't write this in exams, but to memorize, you can write it 1C, 3C bonds. In graphite, what happens? In graphite, we have got one carbon attached to three other carbons. And in the form of hexagons. Can you see this? This is the hexagons. And in the form of giant layers. And one layer, if you see, one layer is attracted with another layer by what? By weak attraction forces, which can be easily broken, right? Which can be easily broken. So one layer can easily slide over the other layer, making graphite used as lubricants also. Now, this is very important portion we have to know about the graphite. Okay, we have to understand that when we see graphite, one carbon is attached to three other carbons in the form of hexagons. Now one, and in the form of giant layers. And this giant layers, giant, we have used this word giant again, right? When we use the word giant, means that there are how many bonds? Millions and bonds, right? Millions or billions of bonds. So graphite will be having a high melting point, boiling point, yes, because you have to break all these millions of bonds, right? You have to break all these millions of bonds, and thus we'll be seeing that it will be very high melting point, boiling point. Now come to the electrical conductivity. In diamond we have got one carbon attached to four other carbons. Do you get my point, right? And there's no electron free to conduct electricity. But in this graphite, we are seeing what? In this graphite, we are seeing that one carbon is attached to three other carbons. Agreed? Three other carbons. In the form of hexagons, isn't it? So the fourth electron is free. It did not bond. Did you get my point? Every carbon has got one electron free. We did not bond, because one carbon is attached to three other carbons. So the fourth electron is free to conduct electricity. And thus, graphite will be a very good conductor of electricity. And this electrons is also called as delocalized electrons, because they are not bonded with any sort of bond, right? The fourth electron is free per carbon. Thus, we'll be seeing that graphite will be a very good conductor of electricity. There are millions of electrons. We learned that the electrical conductivity depends upon what? Depends upon the presence of the free ions, or not and presence of free electrons. Now, moving to this part where you know that when we see a word called as allotropes. What do you mean by the word called as allotropes? We have to master that. What do you mean by allotropes? Allotropes are nothing but it is the same element, right? It's the same element having different physical forms, physical state. Is it clear? So this is a very important part. What is allotrope? Allotropes are different forms of the same element, right? suppose I'm giving the example. Suppose allotropes, ozone. See, ozone is also an allotrope, right? Now you're seeing that what are the allotropes of carbon? There are lots of allotropes of carbon we're having. We have got what? We have got the same element but different physical form. See, graphite. It's a grayish color, right? Lubricant. It's slippery. Diamond, made up of elements, same element, carbon. Fullerene, graphene. So we these are the allotropes of carbon: graphite, diamond, fullerene, graphene. Now you have to understand this important portion, that when we utter the word molecule, molecules will be having covalent bond only, and they will be having a fixed number of atoms. This thing I want to highlight to everybody: fixed number of atoms that they should have. Graphite does have it. Does it have a fixed number of atoms? No. A small graphite and a large graphite rod will be having different number of atoms. Diamond, does it have a fixed number of atoms? No, it does not. But if we take fullerene, in fullerene, see, we have got a fixed number of atoms, C60. It got a full fixed number of atoms, C660. So fullerene is called as a molecule because it has got a covalent bond only. Second, it has got a fixed number of atoms. Now come to the part called as graphene. What is graphene? Graphene are only a single layer of graphite, isn't it? This is the technology which humans have reached, right? If you can take out a single sheet of graphite, what we get? We get graphene. Graphene is very important used. Graphene will be also having the same thing, right? One carbon attached to three other carbons, doesn't it? A single layer of graphite is called as a graphene. So graphene will be having the same properties of electrical conductivity, right? They'll be having a good electrical conductivity because 1C3C bonds are there. One carbon is attached to three other carbons in the form of what? In the form of hexagons, in giant layers. So this is a very important portion we have to master, right? That this will be giving you graphene. A single layer of graphite will be giving you graphene. And graphene will be having a high melting point, boiling point. Yes, it will be. Why? Giant layers. They are in giant layers, right? These sheets are in giant layers. So giant, when we utter the word giant, means what? Tell me. Millions of bonds. So graphene will also have very high melting point, boiling point. And graphene is used where? Where do you use this particular graphene? Graphene will be used in what? In the electronic industries. And graphene, you will be stunned to hear this. They are only one carbon thick. Did you get my point? Graphene is only one carbon thick. Agreed? Right? A single layer of graphite. It's a one carbon thick. It's only a one carbon thick. This is a very important. Only a one carbon thickness. But graphene will be very, very strong. They are 100 times stronger than steel. You heard it right. 100 times. You all have to remember one thing. That graphene will be 100 times stronger than steel. And where it is used in? It is used in the computer chips. Right? It is used in the computer chips. Right? Isn't it? And all, right? Isn't it? Fine. Thank you. So graphene is what? Graphene will be the thinnest substances, right? The thinnest ever made. Why? One carbon thick. It's a single layer of graphite. And it will be having an excellent conductor of electricity and thermal energy. Because why? One carbon is attached to three other carbons. So the fourth electron per carbon is free, right? So now this is used where? This is used in computer chips, electronic display, right? And this now come to the part of fullerene. The last allotrope of carbon which you're having in the syllabus, right? Now if you see fullerene, in fullerene, this was discovered, right? This was discovered in 1967 by a group of scientists, right? And this is what? This is what? C60. So is fullerene a molecule? What do you think? Does it contain a covalent bond only? Yes, it does. Does it have a fixed number of atoms? Yes, it does. C60. So fullerene is a molecule. So will fullerene have a high melting point, boiling point? No, it won't. It won't. What's the bonding in this fullerene? The bonding in this fullerene, just look this part. Everybody look, huh? One carbon is attached to how many carbons? Tell me. 3 carbons. Is it clear to you? 1, 2, 3. Is it clear? So the fourth electron per carbon is free. So fullerene, if you see the fourth electron, it's like a football shape. What are fullerenes? We have to know this definition to master. What is fullerene? Fullerenes are hollow-shaped molecules of carbon are called as fullerenes. This is a very important portion to master. Everybody in this group, you have to understand that fullerenes are what? Fullerenes are hollow-shaped molecules of carbon. Hollow-shaped. Master this definition, right? Very good definition, crisply given over here. They're hollow-shaped molecules. So if they are hollow-shaped molecules, they can be of any shape, right? They can be a cylindrical shape. If you're having a cylindrical shape, we call it as nanotubes, carbon nanotubes. So this fullerenes will be having extremely high tensile strength, high electrical conductivity. Because of why? One carbon attached to three other carbons. Thus, they'll be having a high electrical conductivity. Fullerenes can be any shape. I told you, fullerenes are what? Hollow-shaped molecules of carbon are called as fullerenes. And fullerenes can be of any shape. It can be an onion shape, it can be a potato shape, it can be any shaped. And fullerenes are used where? Fullerenes are used as drug delivery, cancer drug deliveries. Right? Fullerenes are used as lubricants. Fullerenes are used as catalyst. Right? This is a very important information we have to know. So if we go back to this portion, we have to know that when we talk about the allotropes of carbon, we have got graphite, we have got diamond, we have got fullerene, we have got graphene. And fullerene is what? A molecule, fixed number of atoms. But all these are not molecules because they don't have fixed number of atoms. And this is the reason you're seeing that we have to master this page, that whenever we have allotropes of carbon, this is a very important portion we have to master, right? So this was all about what? This was all about the gigantic covalent structures and the allotropes of carbon. Fullerene is not a gigantic covalent structure, isn't it? Not a gigantic, it's a molecule, but these are gigantic covalent structures. Now going to this part, we have to now go to the portion of silica, SiO2. If you see silica, silica is there near us, glass. If you see silica, silica is a glass. We have glass. Glass is silica, SiO2. Silica also has got a gigantic covalent lattice structure where what happens? You are having this gray are the silicons, right? You're having the silicon. You can draw like this. See, it's very easy. See, silicon, you draw like this. Silicon, if you draw silicon, silicon is also having a gigantic covalent structure. We draw like this, silicon, silicon, silicon. Now, if you want to draw silica, what do you do? It's very easy. You put oxygens inside it, right? I'm drawing what? I'm drawing SiO2. We put oxygens in the middle. This is a trick I want to tell you, right? We can draw like this easily. Over here, what we do after drawing? We erase this, right? So over here, we have to know the bonding also. What's the bonding of the silica? The bonding of the silica is very important. That if you see that in the silica, means the glass, what's the bonding? We know that one oxygen is connected to how many silicons? One, two. So one oxygen is connected to two silicons, and one silicon is connected to how many oxygens? Four. One, two, three, four. So one silicon is connected to four oxygens in a gigantic lattice structure, and hence glass will be having a high melting point, boiling point, very high melting point, boiling point. Glass, we put glass in the ovens, right? Electrical ovens, or to cook our food, right? Glass has like a very high melting point, boiling point. Will glass conduct electricity? Glass won't conduct electricity. Why? Because silicon, all the electrons are bonded. Silicon is in group number 4, right? All electrons are bonded, and hence no electrons are free to conduct electricity. So if you got a question that what is the bonding of SiO2, you can write that okay, it is having a covalent bond. I agree, but it will be very much appreciated by the examiner if you can write that SiO2 has got a gigantic covalent lattice structure. After writing covalent bond, that SiO2, the bonding is covalent bond, and they are in a gigantic covalent lattice structure. So this was all about what? This was all about, and since it has got a gigantic covalent lattice structure, it will be having a very high melting point and boiling point. This is a very important portion. So this was all about the important portion of the gigantic covalent structures and the allotropes of carbon, and finally silica, SiO2. Thank you so much, everybody. Thank you.